In this segment, we're going to look at some properties of limits. We're also going to look at a very special limit involving a trigonometric function. And finally, we'll take a look at the definition of continuity, which uses terminology from limits. So let's begin with properties of limits. And limits have very, very nice properties in the sense that if you have like a constant multiple, you can pull out the constant. So let's just begin with the definition. If the limit of a function f of x is L, and the limit of the function g of x is k, when you have a scalar multiple, the limit of b times f of x, you can factor out the b, and it'll be b times the limit of f of x, which is L. So the answer becomes b times L. Again, similarly with sum or difference, you can distribute a limit operator over a sum or difference. So the limit of f of x plus g of x is the same as the limit of f of x plus the limit of g of x. And if you know the first one has a limit of L and the second one has a limit of k, the answer will be L plus or minus k. You can even distribute a limit operator over a product. You can distribute over a quotient, and even from an exponentiation operation. And when you have just a constant, say limit as x goes to c of just a constant, let's say 5. In that situation, the answer will be 5 because a constant is like a horizontal line. Y equals 5 is a horizontal line. So no matter what value you're approaching, say this is c, whether you approach from the left or from the right, you're always going to be at that constant value of 5. So that's another property, that limit of a constant is itself. So again, it has very nice properties. You can distribute over pretty much anything, product, quotient, sum, difference, and so forth. So let's do an example. Let's say that you happen to know the limit of f of x as x approaches c is 27. What can you then say about the limit of f of x, the third root of f of x as x goes to c? So one of the properties we saw earlier was the exponentiation property. So our n is 1/3 here. So if you know the limit of f of x, which is 27, so the answer will be basically 27 to the 1/3 power. In other words, 3. Okay, over here we can rewrite this. Again, the limit operator can be distributed over a quotient. So you have limit of f of x over limit of 18. In both cases, as x goes to c. But we already know the numerator, based on a given information, is 27. And limit of a constant is itself, which is 18. Now all we have to do is simplify this expression. So just 3 goes to the top, actually let's do 9. 9 goes to the top 3 times, 9 goes to the bottom 2 times. The answer is 3/2. Over here, again, it's just going to be 27 squared, which I believe you're going to get 729 for that. And over here, again, limit of f of x is 27, so this answer will be 27 to the 2/3. And that is a situation, it's like the third root of 27 all together to the second power. And third root of 27 is 3. 3 to the second is 9. So there we have it. So the properties of limits are just like kind of you would expect them to be, you know, similar to properties of functions. So now we're going to take a look at a very special limit, one that involves a trigonometric function. See if I can find it in the notes here. There we go. Okay, special limit. The limit as x goes to 0 is sine x over x. This limit will pop up in calculus from time to time, like when we learn the concept of a derivative of the sine function. We're going to need that. And some other places as well. So we're going to look at it separately because it doesn't quite follow anything else we've done so far. So if you try to plug in a 0 here for x, you're going to find that sine of 0 is 0. And the bottom goes to 0. So the ratio is 0 over 0, and we learned this is indeterminate. Which means the answer could vary from problem to problem. We just need to do something to resolve the situation, simplify it, so we can actually see what the answer will be. Now, I have a very rough graph of sin x over x over here. Let's also get that graph going on the calculator. So I'm going to go to my graphing calculator, go to your y equals screen, and go ahead and enter sin x over x. But check first the mode, making sure you're in radian mode. Looks like I'm already in radian mode, so going back to y equals sin x over x. So sine of x, close the parentheses for that, divided by x. Now if I graph this to regular rectangle, zoom 6, that goes from -10 to 10, you're not going to see much. It's just going to look like a very empty graph. You don't see much of what's happening. So knowing this is a trig function, I know it's limited between -1 and 1, and then we're dividing it by x. It's getting even smaller. I'm going to change the window. I'm going to make it from negative. First, let me change the y value. So this one, don't worry about that right now. Go to y minimum. I'm going to make that from -1 to 1. So we can see more action, and then go to X window. Here I want to see kind of quite far to the left and far to the right. So I'm going to make it like -20 to 20. And now let's look at the graph. So we can see a lot more. Looks like this graph has a lot of oscillations, and looks like the oscillations are dying down as you move further to the left and further to the right. Now, right at the point 0, because our function was sin x over x, we expect right at that point, basically there's a little hole. You may or may not be able to see that on your calculator. Chances are you won't be able to see it because the y-axis will fill in the hole anyway. But so roughly speaking, this is the graph. As x goes to infinity, the function is going towards 0. The oscillations are dying down, getting smaller and smaller, wrapping around the x-axis. But here we are mainly interested in what happens as x goes to 0. So if you zoom in or trace around the point, like if I click on trace here, and then type something like 0.999, very close to 1, what is happening? The y-coordinate appears to be 0.841. Interesting, converging very slowly. Let me do it again. Let me try point for x. Sorry, x was approaching 0, so I'm sorry, my bad. So let's get really, really close to 0. So it's something like 0.0001. And let's look at the y value. What's happening right around x equals 0 to the y values? Okay, here it's giving us the exact value of 1, but it's really rounding it. If you try like 0.01, the y value is 0.9999. So it's really going to get closer and closer to 1 as you approach to x equals 0 on this graph from the right-hand side. And you can also do the same. Try -0.01. You're going to see it's also approaching to 1, the y values. But if you try exactly 0 for x, excuse me, I keep going back to 1 for some reason. Okay, clear. X equals 0 should be undefined. You see there's no answer for y. So it's undefined at the point. But as you approach to x equals 0 from the left and from the right, the y values are approaching 1. So for this question, we're going to say the answer appears to be 1. And this is an important limit, and I don't want you to waste your time every time, trying to explore it on the calculator, trying to figure out what it is. So I'm going to ask you to try to remember this because it'll prove to be helpful as we're solving some examples. If you can remember this result, the limit as x goes to 0, sin x over x goes to 1. Now you might say, okay, what did people do before graphing calculators, right? Well, of course you could have done, as long as you had tables of trigonometric functions, you could do a tabular approach, like let x get closer and closer to 0 to see how the value of sin x over x varies. But mathematicians, they love proofs. They will not believe you unless you give them a mathematical proof, no calculators, no tables, nothing like that. So in case there are any math majors out there, or in case there are students interested in proofs, I'm going to refer you to your textbook. There is a section somewhere in that chapter, in the limits chapter, and it starts by introducing something called the squeeze theorem, and from there it moves and actually takes like a whole page to prove the limit of sin x over x that is equal to 1. I'm going to just barely touch base on that topic. If you're not into proofs, you can just fast forward this part real quick. But so first the squeeze theorem, which is in itself I think is important. It's good to know. So it's telling us that if you have a function squeezed between two other functions, so f is between h and g, like in this graph, f is squeezed. Some books call this a sandwich theorem. So if f is between h and g, and if you happen to know around the point c, you happen to know the limit of g and you happen to know the limit of h, that they're both the same. Basically, then we're saying that if you know the limit of this and the limit of that, as x goes to a certain value, and if they're the same, that implies basically what's sandwiched in between must have the same limit as well. Here is a statement of it. If h has a limit of L and g has a limit of L, so both of these are going to L, then the middle function must also have the limit of L. And the proof uses this, and basically in their proof they start by they establish an inequality, and to establish the inequality they're using the unit circle, so you may want to look at the details there. But through that, let me just point out to you that they establish this inequality, that cosine theta for values, cosine theta will always be less than or equal to sine theta over theta, which is always less than or equal to 1. And now if you take a limit as theta goes to 0 of all three sides, limit as theta goes to 0, limit as theta goes to 0. Okay, what is the limit of cosine theta? So first, I guess you would check cosine of 0, right? Which gives you a value right away. So that's the limit. Cosine of 0 is 1. Then you have the same quantity as above, sine theta over theta. And limit as x goes to 0 if a constant 1 is itself. So you see we're using the squeeze theorem here. This goes to 1 and this goes to 1. Therefore, the middle part must go to 1 as well. And again, I guess the biggest bulk of this proof is establishing this inequality. And like I said, please feel free to check this out. I'll even leave it here for you to observe if you like, stop it for a few moments. And if you have questions, feel free to ask them in our discussions board. Okay, so for now, we're going to take it as that limit is equal to 1 and do some variations of that. For example, let's do this one. For example, limit of sine of 5x over x. Now, some students mistakenly decide to factor a 5 out of this, which we really cannot do. But somehow, in this situation, you end up getting lucky. If you make that mistake, basically, let me just say that the final answer to this question turns out to be 5. But it's not that because we can factor this 5 out, because you cannot. With trig functions, unfortunately, they're not as nice as limits. You cannot take a constant multiple out of a trig function. But there are other ways to simplify this. For instance, you can multiply the bottom by 5 and the top by 5. So now you have multiplied the entire equation, rather expression, by 5 over 5, which is 1. You haven't changed anything. So if you now group this together, what is the limit of sine 5x over 5x? Well, you can kind of look at this like sine of u over u. And u is approaching to 0 because x is going to 0, so 5x is going to 0. So now, in a sense, we're back to this situation. Sine of a quantity over the same quantity on the bottom. As that quantity goes to 0, that is 1. And the answer will be 5 times 1, or 5. Okay, the next example I want to do is the limit of sine of 4x over 3x as x goes to 0. So the idea is whatever you have up here, if you have sine of 4x, you want to end up with a 4x on the bottom, because as long as these two quantities are the same, and as long as that quantity ends up going to 0, you can make use of this general identity. So there's a 4x up at the top. So what I'm going to do for this situation is multiply. I need a 4x at the bottom, so multiply the bottom by 4, but if you do that, you have to multiply the top by 4. And now you have sine 4x over 4x. It can be grouped together. And that quantity will go to 1. Let me rewrite all of that really quick. Limit as x goes to 0, 4 over 3 times sine of 4x over 4x. And this part, of course, goes to 1 because 4x is going towards 0, and the answer is 4/3. So I guess you get the idea that, by doing this a few times, you're going to see that if you have a limit as x goes to 0, sine of ax over bx, it will always turn out to be a over b. And what about tangent x over x? Well, that is easy to get if you happen to know what is happening to the sine function. So, because you can write tangent in terms of sine and cosine, right? So let's do that. Tangent is sine x over cosine x. And at the bottom we have x still. Of course, the first thing you may want to do is plug 0 in for x at the top and x at the bottom, and you have 0 over 0. You realize you have indeterminate form, and that's when you continue with these next steps, trying to get rid of the indeterminate form. Now this is like x over 1, so I can rewrite the given expression as sine over cosine times 1 over x. And do you see something familiar? Sine x over x. As x goes to 0, we know that goes to 1, right? What about cosine x? Well, cosine of 0 is 1, so the entire expression is sort of like 1 over 1 or just 1. So you may also want to know that one, that tangent of x over x, limit as x goes to 0, that is also equal to 1. And if you have any variations of that, like ax over bx, you have an a and b inside and at the bottom, so ax and bx at the bottom. So it's the same property as sine ax over bx applies. This will be a over b, basically. Now you might wonder, what about limit as x goes to 0 of cosine x over x? As it turns out, this one does not have a limit. And you can easily verify that by, or maybe not so easily really, but you can go to your graphing calculator, graph cosine x over x, and you will see a lot of oscillations around 0. You will see it's not going to a unique value. But what mathematicians have discovered is instead of that one, there is a limit for this quantity, limit as x goes to 0 of 1 minus cosine x over x. And I would ask that again, graph that one also please, and verify that this one is going to have a limit of 0. This one doesn't come as often, so you don't have to necessarily memorize it. Just know that sine x over x as x goes to 0 is 1. That will probably come up more than the others. If this one comes up, you can always look it up, or you can always use your graphing calculator to refresh your memory. But if you were to plug in 0 right away, you would get 1 minus cosine 0, and cosine 0 is 1. And so you would have 0 on the top and 0 on the bottom. Once again, you're starting with indeterminate, and then you do what you have to do to get rid of it. In this case, you can use a table or a graphing calculator. And of course, there are mathematical proofs for that one also. Okay, now we're going to take a look at an example using everything we've learned so far. Let's check this out. How could you find the limit as x goes to 0 of the given quantity? If you like, pause the video here, try to manipulate this a little bit, see if you can kind of simplify it somehow, use things we've learned, see if you can resolve it. And if not, come back for a hint. And again, I would always recommend that you pause the videos often. I think that's really the best learning you can do, by trying to do it for yourself first and then come back and see, to get some hints from the actual video. I'm going to start by plugging 0 in. I have 0 minus 0 over 0 times 1, which of course is 0 over 0 or indeterminate. So we need to do something about this. Let's try to simplify it a little bit. Okay, in simplifying this, I'm going to try to split it into two fractions. 3x over the bottom, it's just a product there in between them, minus sine x over the bottom. So let's look at each one separately. Here I can cancel the x's. I have 3 over cosine x, and as x goes to 0, cosine 0 is 1, right? So there you have 3 over 1, or 3. The second part, and remember the limit operator can be distributed. Look at the second part. And here you're going to recognize the famous one we just did earlier in the previous page. Limit as x goes to 0, sine x over x is 1. And here you have 1 over limit of cosine of 0. And cosine 0 goes to 1 as well. So what we have here then is 3 minus 1, or 2, as our final answer. All right, so that was our special limit. And the last mini topic here is the topic of continuity. How can you define a continuous function using the concept of a limit? You know, up to this point, you could have defined a continuous function in simple words. You could have said, okay, you know, a continuous function is one where there are no jumps, no holes, no asymptotes. You know, if you can basically, you know, start graphing something and without lifting your pen or pencil continue on, you know, we're talking about a continuous function. But in terms of mathematical notation, how can you define it? This turns out to be a very important concept in math. And mathematicians are never comfortable using just words to define something. They need to have equations, very precise definitions. And here's how they define continuity. Okay, so a function f of x is continuous at a point x equals to c if the following conditions are satisfied. There are 3 conditions, and all 3 have to be satisfied for a function to be continuous. First condition, the function itself must be defined at that value. So it cannot be like this. If it's just a hole, you have no idea what's happening there, it's not going to be a continuous function. It has to be defined there, whether it's here or whether it's there, but you have to have a filled in dot. You cannot skip a point, basically. It must be defined. Second condition, limit as x goes to c of the function must exist. So the limit as x approaches to the value must exist. So you cannot have this situation. Because here limit from the left is not the same as the limit from the right. The limit doesn't exist there. So basically this condition is saying, get over here, come down over here, you know, we need you to be here for continuity, right? And the third condition says, okay, this says f of c must exist, limit must exist, and this one is saying the above two must be equal to one another. So if you have those 3 conditions satisfied, you have a continuous function. So let's take a look at these 3 examples. Example number 1. Is this function continuous at c? If not, which of these 3 conditions is not satisfied? Well, let's take a look. There's a hole right above c, right? So this is clearly telling me, number 1, f of c is not defined. So condition number 1 has been violated. What about over here? Well, f of c is defined right here. It's well defined. But does the limit exist? And the answer is no. As you approach from the left-hand side versus the right-hand side, you're going to 2 different y values, right? Limit doesn't exist. So the condition number 2 has been violated. So this is not continuous because number 2 doesn't even exist. Okay, example 3. Here's your function. Is it continuous at c? At a glance, we can see it is not, right? There is a hole in the graph. There's a jump there. So we know it is not continuous. But how would you express it in terms of the definition? Well, is f of c defined? Yes. F of c is defined as such. Maybe that's the point 1. Does the limit exist as you approach from the left-hand side and the right-hand side? The limit exists, and it is equal to, let's say, 2. But the limit is not equal to the function value, right? So the condition number 3 has not been satisfied in this case. That's why this one is not continuous. Okay, and in these 3 examples, again, the question is the function continuous? If not, where is it not continuous? And in addition, we're going to want to know, is whatever is not continuous, is that a removable or non-removable point of discontinuity? And basically, the definition of that is, if you have a situation like this, you have a removable discontinuity because basically, by just redefining that point, Just filling that in. You can make this a continuous function. So this is an example of a removable discontinuity. But if you have a situation like this, this is an example of a non-removable discontinuity, basically when you have a vertical asymptote. Around x equals to 0, basically the function is not even defined. Already the first condition out the window, right? So we cannot even have a definition for f of 0 for this function. This is not continuous, and this is the worst case. It's called non-removable. It's like hopeless. There's no way to make this a well-defined function in one simple step. So non-removable. If you can read that handwriting, of course. Okay, so now let's take a look at this. F of x equals x over x squared minus 1. Now, from algebra, you may remember that if you factor this as x minus 1 times x plus 1, you know right away this function is not going to be continuous at, so these are points of discontinuity, meaning it's going to be continuous everywhere but these 2 points. So and those points are x equals 1, x equals negative 1, because you would set each of these equal to 0, you would get these answers. And are those removable or non-removable? If you look at the graph, you're going to notice these are non-removable. You will see vertical asymptotes across 1 and across negative 1 on this graph. So they're going to be non-removable. And another way to tell that is it doesn't cancel. The factor x minus 1 or x plus 1 doesn't cancel with anything from the top. So in that situation, basically you have non-removable. Again, verify this on your graph if you like, non-removable points of discontinuity. Whereas this one, you have x minus 3 times x plus 3, factors of the denominator. Now in this situation, you could actually cancel the x minus 3's, right? You could rewrite it as 1 over x plus 3. So clearly at x equals negative 3, you're going to have a problem. By setting the bottom equal to 0, you get this, x equals negative 3. And that one is non-removable. That one will show itself as a vertical asymptote. At x equals to negative 3, we expect a vertical asymptote. But what about x equals to 3? The original function was not defined there, right? The original function, if you plug in x equals to 3, was not defined. So there, it must be one of the discontinuities. But because you were able to remove it later on, what happens is basically that one becomes a little hole in the graph. So at the point x equals to 3, you expect to see a little hole. So I'm going to look at this graph on the calculator. X minus 3 over x squared minus 9. So clear the other one. Make sure to use parentheses. X minus 3 over quantity x squared minus 9. Oops, sorry. I forgot they had the new operating system on this calculator. Let's see. Okay, so I want to erase everything after x squared. Okay, and then I want to use the right arrow key to come down. Oops. Okay, x squared minus 9, and then close the parenthesis. And I'm going to go to zoom 6 to see it from a standard zooming rectangle. Okay, so just like expected, at x equals negative 3, there is a vertical asymptote, which you may not be able to see because that's just a graphing aid. It's not really a part of the graph, but basically it's not defined there. And so the graph appears to be on both sides of that vertical asymptote. So you have one on this side, you had one on the other side. So at the point x equals negative 3, you have your non-removable discontinuity. But if you were to zoom in around the point 3 on that same graph, you would find that there's actually a little hole right there, and that one is your removable discontinuity. And if we go back to the graph, and if I say use the trace key, trace, show me what happens at 3, just press 3 and enter. You see it's not showing you any y value. At that point, even though it looks like it's smooth, there is actually a hole on the graph. And finally, let's do the last one. This is a good place for you to pause the video and then come back to look at the answer. I'm going to factor this. And there are two zeros at the bottom. If you set them equal to 0, you're going to get x equals to -2 and x equals to 1. And in this case, x minus 1s can be canceled, right? So that will appear as a hole in the graph. That is your removable discontinuity. And the other one is your non-removable. And basically the same function then can be written like this. So this one and this one are the same everywhere except x equals 1, because at x equals 1, the original function is not defined and you expect to see a hole. So this is your removable discontinuity point, and this is your non-removable discontinuity point. And with that, I'll conclude the lesson. And next time, we're going to talk about derivatives.